And then I will share. Sorry, go ahead.
Oh no, I was just talking to myself. My bad.
Okay. Hey, Gabby, you're here.
I am here. I don't know why I wasn't.
Oh, I can't. Yeah, I can't see you on the little icon
Yeah,
on the screen. It doesn't
I don't
say.
know. There's like I don't know why I'm not showing up.
Okay.
But I'm here, so.
Hey, well, I'm glad you're here. I'm really happy that all of you showed up. It's wonderful. So I'm gonna share my screen. So I thought we would do it this way, and I will just go through it question by question. If you have a question as we're going along, feel free to just interrupt, and I'll try my best to answer any of your questions as we move along. So let's start with question number 1. Which has a couple of functional groups in this compound. You can see that here we have an aldehyde, and this isn't the question, but hey, Elena's here too. Awesome, welcome. So we have an aldehyde, and then we have 3 different amines over here. So we have 1, 2, 3. These are all amines. Anyhow, they're all primary amines. Anyhow, it's got nothing to do with the question, but it's always fun to get a little bit of functional group practice in. If you have your microphone on, if you could mute it, that would be great because it makes a lot of like noises in the background. And then if you have to ask a question, just feel free to unmute it anytime. All right, it says here, predict and label the bond angles for each carbon in the following structure. You may redraw the structure to more clearly illustrate. So somebody has their microphone on. If you could turn it off because we're getting an echo. Anyhow, so we'll take a look at this first carbon here. And this first carbon has 1, 2, 3 sigma bonds, and then this has a pi bond, so it's a double bond. So when we have 2 single bonds and a double bond, that carbon is what we call sp2 hybridized. And the molecular geometry around that carbon is trigonal planar. So this is trigonal planar. And therefore, if it's trigonal, that means that the bond angles, all of these bond angles, I should erase some of this stuff here. All of these bond angles here are, this bond angle here is 120 degrees. Now the other two carbons, the molecular geometry for both of those is tetrahedral. And the reason why is because both of these, the carbon in the middle here and this carbon on the end, they both have 4 bonds. And therefore, both of these carbons are tetrahedral, right? Tetrahedral, okay? And therefore, all of the other bond angles, and we could label a couple of them here, all of these bond angles are 109.5. And you'll remember that when carbon is tetrahedral, all of the bond angles are 109.5. When carbon is trigonal planar, of course, you divide a circle into 3 equal parts and you get 120 degrees. And then the only other possible molecular geometry for carbon would be, for example, if we talked about carbon dioxide, right, which is a linear molecule, the bond angle here would be 180 degrees. All right, so there we go. So that's bond angles for carbons. We've got a little bit of review on functional groups. Question number 2 says alkanes are also known as saturated hydrocarbons. Explain why. Well, the reason why alkanes are saturated hydrocarbons is, first of all, hydrocarbons means they only have carbon and hydrogen, nothing else. But if you remember, the generic formula for an alkane was CnH2n plus 2. And what that means is that if I have, say, for example, 2 carbons and I take 2 times 2 plus 2, so 2 times 2 is 4 plus 2 is 6. So C2H6, that means that a saturated alkane has the maximum number of hydrogens possible. So we could write in here, because, we'll put here, because they have the maximum number of hydrogens possible. There we go. So alkanes. I just want to put this bug in your ear before we move on. When you have cycloalkanes, and we went over this in detail at the very beginning of the class, the formula is CnH2n. because a ring is the same thing as having a double bond. It has the same effect. Anyhow, I thought I would just put that bug in your ear before we move on. Question number 3 says, draw the line angle formula, the condensed structural formula, and the molecular formula for ethane. So ethane, if we draw the Lewis structure for ethane, we know that it's CH3, right? So we go methane and then ethane, which has only 2 carbons, a very simple hydrocarbon. The line angle formula, this is the same thing as saying the bond line formula. That's what I always call it, but it's the same thing. Chemists love to have different ways of naming the same thing. Anyhow, the bond line formula or line angle formula for ethane is simply a line like this because there's only 2 carbons in the molecule. The condensed structural formula, okay, that has to tell us the structure of the compound. So the condensed structural formula would be CH3, CH3, because I've condensed all of the sigma bonds, okay? And then finally, for the molecular formula is just tallying up the number of each element. Now, in ethane, I have 2 carbons and I have 6 hydrogens, so C2H6. Let me show you something that's kind of annoying when you're an instructor in organic chemistry. Of course, you guys never did this, but if I gave you a compound like butane, for example, and I said, you know, show me a reaction with butane, and then my students would just write C4H10. That is the molecular formula for butane. But the problem with just always throwing down molecular formulas and trying to use those instead of structures, whether it be a line angle formula or a condensed structural formula, the problem with that is that C4H10 could be butane, but it could also be isobutane. And the more carbons that you have, the more ambiguous it becomes. Therefore, you can run into a lot of problems by doing that. Anyhow, just to put that bug in your ear before we move on. The next question, I just answered it. It says, what are the 2 constitutional isomers of C4H10? I already told you the first one. So if we have 1, 2, 3, 4 carbons, this is called butane. And then if I have 1, 2, 3 carbons and 1 in the middle like this, there's a couple ways I can name this. The IUPAC name would be 2-methylpropane. There is a common name for it. I don't think we learned it in class, but there is a common name. I'll just show you what it is. It's called isobutane. I won't ask you to regurgitate isobutane on the final exam. No need to do that. You just have to be able to come up with an IUPAC name. So let's take a look at a couple more questions here. It says, correctly name the following compounds. All of these compounds are hydrocarbons. Hydrocarbon. Okay. And when we name hydrocarbons, what's rule number 1? We have to find the longest carbon chain with the most branches. Now, the first one I think is quite clear that we would go 1, 2, 3, 4, 5, 6. So this must be some kind of hexane. The reason why you would not make this carbon number 1 and this carbon number 2 is that then your methyl group, your first methyl group, would come on carbon 3. And if we start numbering like the red scheme that I have, the first methyl group comes on carbon 2. And we always want to go for the first point of difference. And we're looking to give the substituents the lowest possible numbers. So therefore, we have a methyl group on carbons 2 and 4. So this becomes 2,4-dimethyl. We have to prefix it with di because there are 2 of them. And then hexane. And remember, we only use commas to separate numbers, and we use dashes or hyphens to separate letters and numbers. So therefore, there's no space in between dimethyl and hexane. The next one involves, finding the longest carbon chain, which again, I don't think is a great challenge. So we go 1, 2, 3, and of course, I'm going from right to left in order to give this methyl group the lowest possible number. 1, 2, 3, 4, 5, 6, 7. My question to you is, does anybody who's online, you can either unmute your mic or you could just type it in the chat if you want. Who remembers what this guy is called? That big group, dangling off there. Anybody remember what that one is? It contains 4 carbons.
Is that isopropyl?
It's not isopropyl. So
Oh.
isopropyl only has 3 carbons. So an isopropyl would be this, just 1, 2, 3. Okay, attached to this would be isopropyl. Okay, just like if we have this, right? If we have this, this would be isobutyl. Okay, and then if we have this, this is sec-butyl. So this one here, this is called tert-butyl, the tert-butyl group. And then we have, of course, the methyl group. Now, in terms of alphabetization, we've got the 2-methyl and the 4-tert-butyl. If you remember, we ignore all prefixes except iso, cyclo, and neo. So butyl is going to come before methyl. And therefore, when I put this entire name together, I'm going to have 4-tert-butyl, 2-methyl, and since I have 7 carbons in my longest carbon chain, it's going to be a heptane. Heptane. So with that in mind, let's try this last one here. I'll, put a green circle around it. The longest carbon chain here has 1, 2, 3, 4, 5 carbons. Of course, you could have, you don't have to do it that way. If I erase those, you could have said 1, 2, 3, 4, 5, right? There's many paths, but no matter what, you're always going to get the same answer. So we have a 2,2 and a 4,4 methyl, and the prefix for when I have 4 substituents is tetra. So this becomes 2, 2, 4, 4, tetramethyl, pentane. Oops, I'm going to run a space here, aren't I? Anyhow, tetramethyl pentane. That looks like the way I wrote it. Okay. Well, that's a little bit of alkane chemistry. The next one here says, draw the correct line angle or bond line structure of 8-ethyl 2,3-dimethyl decane. And so the parent, or the parent of the molecule is decane, which means it's got 10 carbons. So you should know methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. And I find the easiest way to draw these is as soon as my pen touches the paper, right? I put a dot here. I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's my decane. Now on carbon number 8, I need an ethyl group. So here's carbon number 8, 1, 2, and then I also need methyl groups on carbons 2 and 3. So I'll put one here on carbon 2 and another one here on carbon 3. I think this is why bond line structures are so advantageous to condensed structures. They're just so much faster, and it's a lot more difficult to lose track of the carbons doing that. Okay, let's get into a conceptual question that deals with, oops, I didn't mean to do that, that deals with melting points. And it says here, circle the molecule you would expect to have the lowest melting point and explain why. Well, if we take a look at all 3 of these compounds, you'll notice the first thing in this one here is that it's an alcohol. And when I have an alcohol, alcohols can participate in hydrogen bonding. And hydrogen bonding is one of the strongest types of intermolecular forces. In fact, it's the strongest one that we look at in this class. And if we just review the types of intermolecular forces, the bottom of the barrel, the weakest ones are the London forces, which result from interactions between nonpolar molecules, so London forces, and then we go to dipole-dipole forces, dipole-dipole, and then on top of that we have the hydrogen bonding. So these are the intermolecular forces that we're concerned with in Chemistry 102. Now, the reason I brought that up is if you look at this molecule here and this molecule here, these are both hydrogens. hydrocarbons. And whenever you're dealing with a hydrocarbon, you can just say right away, the only intermolecular forces that two hydrocarbons would experience for each other would be London forces because they don't have any polar bonds. So hydrocarbons, you could put here, same thing as nonpolar. Well, then, again, it becomes a battle between these two molecules. So which one of these would have a lower melting point? Would it be the one on the top or the one on the bottom? Could anybody answer that? Or does anybody have a good guess?
I said the one on the top.
I agree with you. And the reason why is based off of surface area, right? Right, we could put here lowest, or we'll put here lower melting point because of less mass, right? It's a lighter molecule, it's smaller, less carbons, less hydrogens, and less surface area. Surface area, right? What's melting point? Melting point is when you take something from the solid phase and you convert it into the liquid phase. Well, in the solid phase, molecules are much more organized, right? They're going to be packed very close together, and there's going to be very little molecular movement. And what happens is we increase the temperature, the molecular motion is going to increase until it gets fast enough that, or rapid enough such that the intermolecular forces can be broken. And since there's simply less surface area in a smaller molecule, because both of these molecules are just straight chains, right? So it's just based off of surface area. Hopefully you remember that one time in class, I went over this with you and I explained this in terms of Velcro, right? I said, if you have a piece of Velcro that's only 1 inch long, right? And it's attached to another piece of Velcro that's 1 inch long, there's a certain amount of energy associated with ripping those two pieces of Velcro apart from each other. Now, if I have a piece of Velcro that's, 10 feet long, let's say, and another piece attached to it, they're held together by the exact same type of force, but it's going to take more energy to pull this one apart. Why? Just because of the increased number of interactions or forces between the two pieces of Velcro. And the same rationale applies for linear hydrocarbons. Okay, question number 8. Question number 8 says, what type of isomers are the following molecules to each other? Name the molecules. Well, the first thing you can see is that they're both cyclobutanes, and they both have methyl groups on them. Now, if we go like this, if we say 1, 2, 3, and then we could do the same thing here, 1, 2, 3, we could call both of them 1,3-dimethyl, 1,3-dimethyl cyclobutane. But there's a difference between these two molecules, right? A big difference. Okay, and how would we describe the difference between these molecules? Well, these two methyl groups are on the same face of the molecule. Does anybody remember the prefix that we use to describe two groups that are on the same face of the molecule?
Cis.
Absolutely. Right, so this is cis 1,3-dimethyl cyclobutane, and this one here is trans. It's trans 1,3-dimethyl cyclobutane. Okay, there we go. And how would you compare these two molecules in terms of each other? Well, they are connected in the exact same way, right? They're both isomers of each other. Okay, they're not constitutional isomers because their connectivity is the same. It's the arrangement of the atoms in space that differs between the two of them. So these are, we'll put here, they are stereoisomers, okay? Because, we'll put here, because they differ in the placement of atoms in space. Okay, you didn't have to put the exclamation point. More specifically, these two molecules are actually diastereomers. But I don't think I'm going to ask any questions about diastereomers on the final exam. You should know what stereoisomers are. There we go. So stereoisomers, got to know what stereoisomers are. Okay, write the condensed structural formula of 3-nonene. Well, I always like to start these kind of questions by doing a bond line structure to start with. It's just the way I roll. Now it doesn't tell us that it's whether it's cis or trans. So we're not going to have to be concerned with that. So let's just write the condensed structural formula. So we'll put CH3, so that's the first carbon, second carbon, third carbon. This is where the double bond will be from the alkene. So we'll put CH, our double bond, and then another CH, and then we're going to have, so we've got 3, so we need 6 more carbons. We've got 1 here. So therefore, we can put CH2, and we could put this in brackets. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. If you had written this CH3, I'll put or. If you just wrote the whole dang thing out, CH, like this, that's perfectly acceptable. What does it mean? It means to me that you understand the concept, right? Okay. We've talked about geometric, or no, we didn't talk about geometric isomers already. But anyhow, I digress. So let's see if we can name these two molecules. We'll find the longest carbon chain in both of them. We have 1, 2, 3, 4, and then this one we have 1, 2, 3, 4. They both have a bromine on the first carbon, so they would both be 1 bromo, 2 butene, and then this one here, I'll color code it. This one would be 1 bromo, 2 butene, and it's hard to tell your voices over the computer, but I think it was Gabby who said, cis up here, and we can use the same rationale here because in this first molecule, the 2 hydrogens are on opposite faces of the molecule, so we would call this trans 1 bromo 2 butene, and in the second molecule, the 2 hydrogens on this double bond are on the same side of that double bond, and therefore we would call this cis 1 bromo 2 butene. All righty. And so what type of isomers are they? What type of isomers? These molecules would be considered geometric isomers because the connectivity is the same. They differ in their shape. All right, there we go. Geometric isomers. Name the following molecules. I put a lot of nomenclature in these, so we'll try the first 2 for fun, and I'll post up the solutions to these. So if we take a look at the first one, what's the strategy we're going to take when we have to identify the name for a molecule? Well, I would start by numbering 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I won't give you any 12 carbon chains on the on your exam. I'll just help you out with this one. It's called, so after decane, you have undecane, and that's for 11. And then when you have 12 carbons, it's dodecane. So dodecane. And of course, this is going to be a dodecene and a 3-dodecene. And these 2 hydrogens are on opposite sides of the molecule, or opposite sides of the double bond, I should say. And therefore, this will be trans 3-dodecene. Trans 3-dodecene. And I made a mistake in one of my slides here. So dodecene. So you can try the next one. I'm getting a new prescription. I can't see. Dodecene. There we go. The next one is another alkene. So we identify the longest carbon chain that contains what? That contains that double bond. So we're going to have 1, 2, 3, 4, like this. Again, this is another example where you could have gone this way for number 4 or this way. Either way, you get the same molecule. So this is a 1-butene, some kind of 1-butene. And then we have 2 methyl groups on carbon number 3. So we would call this 3,3-dimethyl 1-butene. We got time. Let's give the next one a shot. This is an alkyne. And of course, the same strategy with alkenes is that we want to find the longest carbon chain, but we need to give that triple bond the lowest possible number. And thus, I will start numbering with carbon 1, 2, 3, 4, 5, 6. So I have a 1 iodo, and I have a 4 methyl. Well, alphabetical order. I and M. I comes before M, and therefore this will be 1 iodo, 4 methyl, and this is going to be 2 hexyne. 2 hexyne, and of course you could also call it, hex 2-ine is fine as well. Either one works. Okay, let's see, we're half an hour in. Where are my students at? What's going on here? Well, I thought I could broadcast my camera, but apparently I can't. Okie doke. Let me see here. Okay, just checking to see who's online. Okay, well, let's keep moving along here. Let's try the next question. Question number 14. Draw the structural formula for 2,2,4 trimethylpentane. We'll draw the bond line formula. And if we have a 5-carbon chain, pentane, right? Pent is for 5 carbons. So we'll start 1, 2, 3, 4, 5. And then on carbon 2, we have 2 methyl groups, 2, 2. And then on carbon 4, we also have 1. And there we go. We're done. Again, we can see the power that bond line formulas have. Let's take a look at this one. This is a great question. This is a very common ACS final type question for Chemistry 102. It says, which one of these is going to have a higher boiling point? Will it be 2-methylbutane or pentane? Let's take a look here. So we'll draw 2-methylbutane. Oops. So let's see here. 2-methylbutane will be 1, 2, 3, 4. 2-methylbutane versus pentane, which is 1, 2, 3, 4, 5. Which one of these would have a higher boiling point? Does anybody have an idea which one of these would have a higher boiling point? Another way we could ask this is to say, which one packs more efficiently? Right? Because they're both hydrocarbons. So again, the only thing they're going to experience will be London forces. Well, think about it. If I have another molecule of 2-methylbutane, how well are they going to pack together compared to this guy? Right? They're going to pack together perfectly, right? Right? They're going to pack together super duper well. Whereas these ones, it's not as easy to pack them together. You can get them close together, but they're never going to pack as efficiently. So both are C5H12, but pentane packs more effectively, therefore more intermolecular forces, right? Therefore higher BP. That's it. Okay, let's get into some good old Zaitsev and Hofmann elimination here. Draw the possible products that will be formed when the following molecule is dehydrated in the presence of a strong acid and just cooking it up, right? So what are you doing? You're going to do a dehydration. This means loss of H2O. Now, if I examine this alcohol, I'm going to treat this as concentrated acid and I'm going to heat it up, and I'm going to remove water. We could even write this in here, minus H2O, just so, you know, we can keep track of what the hell we're doing. Well, what's H2O made of? It's made out of OH, which we have here, and then we need a proton. And you remember that the way I taught it to you in class is I said, you go next door, right, to this carbon, and you say, okay, it's got a hydrogen, so I could remove that hydrogen. And if I did that, and I'm just going to draw the bond line structure, you would end up with this molecule, right? That's the molecule you would get if you pulled off the atoms that I circled in blue. If we erase that, if we were to remove this, again, if we removed the hydroxyl, and if we move this sorry, I thought I was using red. There we go. This one and this hydrogen, then I'm going to form my double bond here, right? So let's draw what that product would look like. Well, it would look something like this. Can anybody tell me which one of these would be the major product? Would it be the one in red or the one in blue?
So would it be the blue one because there's more hydrogen? I mean, yeah, more hydrogens connected to that one.
No, it's the opposite,
Oh.
right? So yeah, so Zaitsev is the more, I'll write it down here. I'll write it in black. So we'll put Zaitsev product is most substituted alkene. Okay, the most substituted. If I look at this alkene, it's got 2 hydrogens attached to it, whereas this one only has 1. So let me just help you out with this. The more substitution, right? An alkene can have a maximum of 4 groups on it. The more groups that you have, the more stable that they become. So if you go from 4, it's going to be more stable than if you had 3, which is going to be more stable than if you had only 2. Whether they're cis or trans, I'll just draw a cis for the hell of it, which is going to be more stable than if you had only 1. So the more hydrogens you have attached to it, the shittier it is, pardon my language. And therefore, the most substituted one, this one here, this is the Zaitsev product, and this will be the major product. Major product. Does that help?
Yeah.
Okay, good.
Yes.
Great. If there's anything else, because you can be sure I'm going to ask a question about Zaitsev, right? It's one of those things. I'll ask a question about Zaitsev for sure, at least maybe 1, maybe 2, and maybe 1, maybe 2, but Markovnikov, right? These are things that you got to know when you come out of this class. If you were to write the Hesse, for example, you would have to know Markovnikov addition. And with that, that's a good segue to take us to the next problem, which deals with determining Markovnikov addition across a double bond. It says draw the possible products that will form when the following molecule is reacted with HCl, hydrochloric acid. So this is a case where we're doing, addition of HCl across a double bond. And remember, Markovnikov, I'll just put Markovnikov addition. We follow the rule, the rich get richer. Okay, well, if I look at these 2 carbons, this carbon has no hydrogens. The carbon in red, that has 1 hydrogen. So that will take this hydrogen as well. And so when we write out the bond line structure, which is what I'm going to use, this is the skeleton of the molecule, but this hydrogen is going to go on this carbon, and the chlorine is going to go on this carbon. Oops, kind of uglied that up there, didn't I? Anyhow, it's going to go on this carbon, so we could just write it like this. This will be the product of Markovnikov addition. Markovnikov product, okay? You have to know Markovnikov addition, and you have to know the rule, the rich get richer. All organic chemistry students have to be cognizant of that rule. Let's take a look at some aromatic compounds and practice a little bit of nomenclature on those. Questions 18, 19, and 20. So let's see here. The first one, there's a couple of ways that I would accept for you to name this. You may remember, may not, and it's okay if you don't, because I don't think xylene is going to come up on the exam, but I did teach you this in class. We looked at it one time. I said, if you have this molecule, oops, You get a darker color. If you have this molecule, you have a benzene ring, and then you'd put a methyl group on it like this. This is called toluene. Okay, and then I said if you put a second methyl group on it, it's called xylene, Xylene. Okay, so there's three types of xylene. There's ortho, meta, and paraxylene. And since these two methyl groups are 1, 2, 3 carbons apart, this is called metaxylene. And again, if I'd asked you this question and you wrote 1, 3 dimethyl benzene, I would accept that. Absolutely. I guarantee you that's what it says on Wikipedia. When you look it up, it's probably got a whole bunch of names. The next one is an interesting one. We saw this group earlier this evening, and we identified this as a tert-butyl group. Okay, so we know the tert-butyl, but then we have the two bromines, and the question becomes, where do we start numbering? Do we call this 1, 2, 3, and 4? Well, remember, with nomenclature, when we're numbering on an aromatic ring like this, we want to go for the first point of difference. So if I number this way, my groups are at carbons 1, 3, and 4. If I change that, so I'm going to erase all that. If I do it like this, I'm going to try it. Hold on. Boom, fixed it. All right. If I start numbering here, then I have 1, 2, 3, and 4. Then I have 1, 2. And 1, 2, so 2 is a lower number than 1 and 3. Therefore, this is the correct way to number these. So I have a 1, 2 dibromo, and I have a 4 tert-butyl. But bromo, Br, comes before butyl, Bu. And so this molecule becomes 1, 2 dibromo, 1, 2 dibromo, 4 tert-butyl. Oops, didn't mean to do that. 4 tert-butyl. Benzene. You might remember that another way of drawing benzene, right? If you draw it with the 3 bonds, you can also draw it like this with a circle in the middle, like that. That's perfectly acceptable. So this is another benzene derivative. This one's kind of not a jerk question, but it just kind of becomes a question of how do you number this, you know? And we have an iodo group here. We have a butyl, and we have a methyl. Now, however you do it, it's going to be 1, 2, 3, or it could be 1, 2, 3, right? So it's going to be a 2-butyl. So should it be a 1-methyl or a 3-iodo? And when we have a tiebreaker like that, we go with alphabetical order, and therefore we would name it like this. We would have 1, 2, 3 like that. So we would have 2-butyl, 1-iodo, 3-methylbenzene. But there's a better way. Does anybody recognize a piece of a molecule in here that we talked about a whole bunch of times in class? Pixel eraser. That's what I want. Does anybody recognize a common molecule? What if I circle it? Oops. Let's circle this.
Isn't it drawn up top, the toluene?
Exactly. You're 100%. It wasn't a trick question, right? I don't like trick questions. You're absolutely right. So we would name this as a toluene derivative, right? So if we name it as a toluene derivative, then this, where the methyl group automatically becomes carbon 1, then we have a 2-butyl and a 3-iodo. And that's a better way to name it, in my opinion. In fact, I'm only going to write that one down. So we'll put here 2-butyl, 3-iodo, toluene. Okay, there we go. The next question says, write the condensed structural formula. Oops, didn't mean to do that. Write the condensed structural formula of 3-methyl-1-pentanol. So 1-pentanol has 5 carbons. So let's start at 1, 2, 3, 4, 5. On that first carbon, I'm going to put an alcohol, right? OL means alcohol or a OH group. So I need to put that on here like this. And then I have a 3-methyl. So I go 1, 2, 3, and then I put my methyl here. Comme ça. There we go. And then it says, write the condensed structural formula. So let's write the condensed structural formula because that's the bond line structure. Sorry, I'm seeing double here. I need to do prescription. So let's try drawing it out. So we'd have a hydroxyl. Then we'd have two methylenes, right? There's one here. There's another one here. So we'll write those in. Then we have a CH, a methine, with a methyl group attached to it. And then we have CH2 and CH3. All right. There we go. It gives us a couple more molecules to try drawing. 4-methoxyoctanol. I don't know why there's a space here. There shouldn't be a space right there in between those two. But let's give it a shot. It's an octanal. So when I have an al, this means it's an aldehyde. An aldehyde. So 4-methoxyoctanol. So let's go 1, 2, 3, 4, 5, 6, 7, 8. And we'll put the aldehyde here on the, we'll call that the first carbon, and then on carbon 1, 2, 3, 4. So on carbon 4, I'm going to put a methoxy. And a methoxy is when I have an oxygen and a methyl group like this. So there's my methoxy. The next one is 3-methyl-2-pentanol. So this is an alcohol. And we have 5 carbons in the main chain. So we'll go 1, 2, 3, 4, 5. It's a 2-pentanol. Therefore, my alcohol is going to be on the second carbon. And then on the third carbon, I have a methyl group. 3-methyl-2-pentanol. And the last one is 2-ethoxybutane. So butane, again, 4 carbons. 1, 2, 3, 4. And then on the second carbon, I'm going to put an ethoxy group. So I have an oxygen and then ethoxy, right? If you have this, right, this is a methoxy. If you have this CH, right, like this is an ethoxy. Obviously, if you add a carbon to that, I'm sure you're all ahead of me. This is called propoxy. Okay. All right. Let's take a look at question number 25, which asks, circle the molecule that would be the most soluble in water. I'm going to draw the bond line structures very quickly, just so we can get a bird's eye view of what they all look like. So 2-isopropyl hexane, 1, 2, 3, 4, 5, 6 for my hexane. And then on carbon 2, I put an isopropyl group. Again, you have to know how to draw an isopropyl group. So this one is just a plain old alkane. The next one says 2-tert-butyl-1-pentanol. So I have my alcohol 1, 2, 3, 4, 5. And on carbon number 2, I put a tert-butyl like this. And the next one is non-enal, which is, again, an aldehyde. So I'll start out with my aldehyde, and then I'll put 1, 2, 3, 4, 5, 6, 7, 8, 9. And the question again asks us which would be most soluble in water. So we have an alkane, an alcohol, and an aldehyde. Can anybody guess which one of these would be the most soluble in water?
Would it be the alcohol?
Absolutely. Yeah, absolutely. It would be this one. So they all have 9 carbons, right? So they all have a similar molar mass, or at least they're not different by leaps and bounds here. We're not comparing an oil and, methane. We're just comparing 3 molecules that are similar in terms of molar mass. But what's the difference is that Gabby said that this compound, the alcohol, is capable of hydrogen bonding, right? Because it has an OH group, and therefore it should be the most soluble in water, the alcohol. Remember the rule, like dissolves what?
Like.
Thank you. I love that intonation. All right, there we go. So it's 6:20. Let's keep rocking and rolling here. Into 3 hours. Draw the reaction that converts propene to isopropanol. This isn't meant to be anything, it sounds kind of intimidating, but propene is just, if we take propane and we put a double bond, so this is propene. We don't have to give it a locant. We don't have to call it 1-propene because there's only one place to put a double bond in propene. And if we want to convert that to isopropanol, you should know how to write out the bond line structure for isopropanol. So this is isopropanol, which is the same thing as isopropyl rubbing isopropyl alcohol. This is rubbing alcohol. And I even had a whole slide on this in the alcohols chapter where I went on a whole dog and pony show about how you do that. Well, you can see that all that's happening here is a Markov-Nikov addition, right? Markov-Nikov addition of H2O across the molecule. And what do you need to do that? You need to have an acid catalyst and you need to have water like that. Normally when acid is a catalyst, we put it inside these square brackets like this. If you didn't understand that, I would never ask you a question that's going to confuse you on square brackets. So again, it's just a Markov-Nikov addition of water, right? The rich get richer because if you look at propene, right, this double bond has 3 hydrogens. This is the richest carbon, and it's going to take on the extra hydrogen, so now it becomes a CH3. Anyhow, just a little tutelage there. All right, let's take a look at another one that involves a reaction. Draw an example of a hydrogen bond. Draw an example of a hydrogen bond between ethanol and water. Sorry, it's not a reaction. It's just asking you to represent hydrogen bonding. Oops, I didn't mean to do that. I think that any student in this class should be able to, go up to somebody in Chemistry 101 and explain hydrogen bonding to them and draw it out efficiently. So let's start by drawing a molecule of ethanol. I'll use the condensed structure, and you remember that this oxygen has a bent molecular geometry. We're going to include the lone pairs, and remember that this oxygen is delta minus because oxygen is the second most electronegative element in the periodic table. It's going to pull more electron density towards itself in that covalent bond, which is going to render the hydrogen delta plus. And of course, in our hydrogen bond, we're going to show the hydrogen bond between the lone pair of an oxygen atom and a hydrogen atom, which is bonded to an oxygen atom. So now let's draw a molecule of water. Again, there are Avogadro's number of ways that you could have written this down on the piece of paper. I'm just choosing to draw it this way, and I will choose red as the color to represent my hydrogen bond. So I'll put a dash between a lone pair on that delta minus of ethanol and the delta plus on my oxygen of water. You could put in some more molecules if that floats your boat. So we could put in another molecule of ethanol like this. And maybe with this one, I sound like Bob Ross. Maybe this one wants to do, maybe he wants to do a hydrogen bond to, I don't know, this one over here. And then it wants to do another hydrogen bond like that. And then you have another water molecule. Oh, I changed colors, didn't I? Shouldn't have done that. Anyhow, maybe I want to have another water molecule over here. Anyhow, Bob Ross should be doing this. It's your playground. Make the hydrogen bonds where you want them to be. This is your scene. Okay. Anyhow, again, everybody in this class should come out of Chemistry 102 being able to represent hydrogen bonding and being able to explain it to a friend or a loved one. Question number 28. That's kind of an interesting question. This one's kind of a head scratcher because I never addressed this question directly in class, but you can figure it out based off of the principles that I went over in class. And that's part of what being a good scientist is being able to take your knowledge and being able to apply it to something that you've never seen before. So it says here, which would be expected to undergo dehydration at lowest temperature? So removal of water at lowest temperature. A primary, secondary, or tertiary alcohol. Well, if we just take a look at a primary alcohol, and I'll just do this one quickly, just for the interest of time. But if we had, let's say, propanol versus, let's say we had, one propanol, then we have one methyl, one propanol, and then we have, I don't know, then we have something like this. So there we go. Like that. So, sorry, the first one is 1 propanol. The second one is 2-butanol. And the next one is 2-methyl 2-butanol. Sorry, Mr. Deon is getting tired. Anyhow, if I do a dehydration, the thing is that if I dehydrate the tertiary alcohol, okay, by taking it and treating it with a catalytic amount of acid, and I heat that up to drive off the water, what I can form is a major product that I would get would be this alkene. Whereas if I took this compound and I did the same thing, I would end up with an alkene like this. And if I did it with the primary, if I did the same thing, I would end up with propene. And which one of these three alkenes is the most stable, right? Do you remember all the way back here? I said the more substitution that you have on an alkene, the more stable it is. And therefore, the faster the reaction will proceed. It's much easier for the molecules to get to the finish line, if you will, of the reaction to make the more stable compound. And therefore, based off of that rationale, the question that, or the reaction that would proceed the fastest would be this one, because we'll put here most substituted or most stable alkene is formed. That's all they're getting at in this question. This question was actually written by a friend of mine at Metro State University in Denver. I thought it was a pretty fun question. Question number 29, draw the possible products of dehydration of the following molecule. So this, in this case, and it says products, we're going to identify both the Zaitsev product, right, and we're going to identify the Hofmann product. And you remember that the Zaitsev product is the most substituted alkene. So if I take this, I treat it with a catalytic amount of acid and I heat that up, I'm going to lose water. How do I lose water? Well, let's draw both of them. If I look at this carbon, this is called the carbonyl carbon. I went over in that in class many times. I look at the two next door neighbors. Let's start with this one. This has a CH3. If I remove one of those protons, I would end up forming this alkene. Okay, I'd form one hexene. If I was to remove one of these protons over here that I've written in blue on this methylene, then I would end up with this molecule, which is 2-hexene. Which one of these, the red one or the blue one, which one is the Zaitsev product? Is it red or blue? Zaitsev.
So isn't it the red one because it gets richer?
No, it's not. So remember, Zaitsev is the most stable alkene. Okay, so Zaitsev, put here, Zaitsev is the most substituted alkene. Most substituted, therefore most stable. Most stable. Okay, the rich get richer rule only works for Markovnikov addition. Don't try to, and I'm not saying you're trying to do this, but don't try to retool it for elimination reactions. For elimination reactions, which is this type of reaction where you're losing water, right? Because to balance this equation out, I'd have to put plus H2O. I just chose to write it under here. Anyhow, when I remove water, I examine the two possible alkenes. Well, this alkene is di-substituted, right? It's got a carbon here and a carbon here. This alkene is only mono-substituted, only one measly carbon. Therefore, this one is most stable. Therefore, this is the Zaitsev product. Oop, there we go. Does that help?
Thank you. Now I remember that.
Okay, great. Yeah, that's why we're doing a review. You know, I've taught this class. This is, I think, my 10th or 11th time teaching this class. I've taught this class enough to know that at the end, everybody needs a little refresher in all the concepts in organic chemistry, which you knew at one time. But hey, you know, it's the first time you take the class. I don't expect you to remember everything you ever learned in it. And that's exactly why we focus on organic chemistry. By the way, BTW, most of the final exam is organic chemistry. There's only a certain percentage of it that's biochemistry. I think it's around, 35% biochemistry and about 65% organic chemistry. So let's take a look at question number 30. It says, circle the molecule that would be expected to have the lowest boiling point and explain why. What is this about? This question is about our good friend, right? Whenever we're talking about boiling points, melting points, it's got to do with IMFs, intermolecular forces. So if I draw 1-pentanol, I think we've drawn it several times this evening already. So 1, 2, 3, 4, 5, good. Pentanal, Draw a pentanal. That's an aldehyde. 1, 2, 3, 4, 5. 1 ethoxypropane. So let's put this here. So there's my 3 carbons, and then I have an ethoxy group like this. That's good. And then the next one is 3 pentanone. 1, 2, 3, 4, 5. And then I have this. So I go from, I've got a ketone, I've got an ether, I've got an aldehyde, and I've got an alcohol. And it's asking me which one would take the least amount of energy to boil. Now, I asked you a question on the first exam and the second exam where I gave you a carboxylic acid, an alkane, an aldehyde, an alcohol, an ester, and a ketone, an ether. And I said, rank them all in order of boiling point. And there's one of these that has a higher boiling point than any of them for sure, and that is the alcohol. I'm pretty sure you could all identify that. So this one has the highest BP. But which one of these other 3 is kind of the loser, the lowest boiling point? Who remembers?
Is it the ether?
Absolutely. I think that was Tony, and you're right. Okay, it's the ether. And the reason why is and this is something that it's kind of memorization, but it has a very weak dipole. Okay, the dipoles in an aldehyde and a ketone, they're strong on that carbonyl, whereas in an ether you kind of have like a dipole going this way, and then you get another one going this way, and then they add up together like that. So it's just weaker because the dipole is flanked by those 2 alkyl groups on either side. There you go. Now I'll just put this bug in your ear. I told you that between a ketone and an aldehyde, they have the same number of carbons. There's no way to distinguish which one would have the higher or lower boiling point. Very difficult to do. Okay, number 31. Which of the following compounds will undergo oxidation with potassium dichromate? Potassium dichromate is just a really strong reducing agent. It's K2Cr2O7. Just we'll put here strong oxidizer. Okay, to form a carboxylic acid. While you're trying to figure that out, I'm just going to go quickly and get some water, and I'll be right back. All right, I'm back. Yesterday I was out walking around and got a horrible sunburn. All right, hurts to move. Anybody figure this one out? Which one of these would be oxidized to a carboxylic acid?
Wouldn't it be the aldehyde?
Absolutely. Yeah, I went over that a lot in class, where you could take a primary alcohol, right? You could take a primary alcohol, oxidize it to an aldehyde, and then I told you it was kind of hard to get it to stop there. It can be further oxidized to a carboxylic acid. So the answer is the aldehyde. You could take that aldehyde, I'll just draw a funny reaction arrow like this, put our potassium dichromate, and we could oxidize that to, this is called cyclohexane carboxylic acid. Yeah, so we could oxidize that. The 2 ketones, there's no way to oxidize those any further. Nothing that we learned in class anyway. Okay. Explain the reason why you can't oxidize a ketone to a carboxylic acid. The reason why it doesn't work is if we draw out the structure of a ketone, let's say we have something like this, okay? The reason why is because there are no alpha hydrogens. And what an alpha hydrogen means, there's no H's, we'll put here no H's directly attached. Okay, and we call those alpha hydrogens. Okay, in an aldehyde, right? In an aldehyde, I would have something like this. Okay, this here, this is an alpha hydrogen. Okay, so this is comparing again a ketone versus an aldehyde, and that's why you can oxidize an aldehyde. Got to have an alpha hydrogen. The next one deals with keto enol tautomerization. Let's take a look. I would never ask, I don't like the way this question is phrased. I'm not a huge fan of it, but let's just take a look at it. It says, will this compound undergo keto enol tautomerization? So 2,4-dimethyl-3-pentanone. So if we have 1, 2, 3, 4, 5 pentanone, 3-pentanone, and then we have a 2-methyl and a 4-methyl. So that's the molecule, and the answer is yes. Okay, so what a keto enol tautomer is you go next door and you look at one of the hydrogens, and then you draw the equilibrium like this, and then you put a double bond between the carbonyl carbon and the carbon with that hydrogen in red, and it would look something like this. You're basically just moving the double bond in a hydrogen around. So the answer is yes. What I would rather you be able to do is just recognize an enol, and be able to recognize, an enol. And the reason we call it an enol is because it has an alkene and then it has an alcohol. So that's why we call it an enol. All right. This next question is a real classic for Chemistry 102. Everybody has to know hydrogenation. It says here, write the product or products of the reaction below. What is the name of this reaction? I guess I was already a little bit ahead. This is called hydrogenation. Very dangerous reaction if you're a cigarette smoker. But if you're not, and you're not smoking in the lab anyway, it's quite safe if you know what you're doing. So we take an alkene and then we treat it with hydrogen. And remember, we can use platinum, or we could use palladium, or we could use nickel. All three of those metals are acceptable catalysts. And what do? Is we add 2 hydrogen atoms to the molecule. So we'll draw the final product out like this. So we go from an alkene to an alkane. This is a reaction that is usually quite well appreciated by my students, and they usually do exceedingly well in any questions that deal with hydrogenation. So this would be 2-methyl butane. It's not asking us to name it, but what the heck. Question 35 says, draw the bond line structure of 2-methyl propyl butanoate. Oh boy, butanoate. What's that? Who could tell me what functional group is going to be in this compound? We drew a lot of 08s one night. I remember. I was there. Before this whole, I'm here. Hey, Sean, great. Thanks for showing up. No problem that you're late. We're just happy you're here. By the way, Sean, and if anybody else is here late, I will post the recording to D2L. I'll post a link to that, so you'll all have access to it, as well as will the students who are unable to attend this evening.
Okay, thank you.
No problem. So I was just asking the class, does anybody remember which functional group is 08? Butanoate. What functional group would I find in a butanoate? I'll give you a clue. Starts with S, ends with ter. It's an ester. Okay, so this is an ester. And the way, so if you're unsure about ester nomenclature, I would take a quick peek at it. So butanoate means our ester has to have 4 carbons. So in the chain, so we have 1, 2, 3, 4, and then we have this, and then the 2-methylpropyl, that comes from the alcohol portion. So 2-methylpropyl would be 1, 2, 3, and then it would have a 2-methyl on it like that. 2-methylpropyl butanoate. So make sure you take a look at ester nomenclature if you're unsure, because they expect you to know about esters when you come out of this class. Name the following molecules. The first one is a carboxylic acid. If you remember, I taught you 2 ways to name those depending on the number of carbons. If it's anywhere between 1 and 5 carbons, you have to know the IUPAC naming system as well as the common naming system. So we'll try both for this molecule. If I look at the longest chain, it has 1, 2, 3, 4, 5. So I have an ethyl group right here. So I could call this 2-ethyl pentanoic acid. That's one way of doing it. Another way was, if you remember, we had alpha ethyl valeric acid. Maybe I should write this down. This is the common way, and this is the IUPAC way. Okay, let's take a look at the next one. The next one, my longest carbon chain is 1, 2, 3, 4, 5, 6 carbons like this. I have, if I had numbered it going the other way, 1, 2, 3, 4, 5, 6, either way, I would have had a substituent on carbon number 2, but then I searched for a tiebreaker. And having the next substituent on carbon number 3 is better than having it on number 4. So let's erase all those red numbers. There we go. And so we have a 2-bromo. Sometimes I like to make a laundry list. Let's do it. We have a 2-bromo, and we have a 3-iodo, and we have a 5-methyl. Hey, what do you know? They're in alphabetical order, right? So I have B, I, and M. They're in perfect order. And then, of course, since I have 6 carbons in the chain, it's a hexane. So let's write down the name, which would be 2-bromo, 3-iodo, 5-methyl hexane. And there we have it, folks. Okay, draw the line angle formula of hexadecanoic acid. This one's not a great question, okay? Hexadecanoic acid is just a fatty acid with 16 carbons. Okay, so you take decanoic acid, which is 10, and you add hexa, you add 6 to it. So this is kind of a silly question. It would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There you go, done. Kind of a silly question. But the next question is not silly. Which would you expect to have a higher melting temperature? Decanoic acid. Let's write out the structure of decanoic acid. So we'll put here decanoic acid. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or cis-dec-6-enoic acid. Let's give it a try. So it would look something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it would look something like this. So we'll call this one number 1, and we'll call this one number 2. Which one of these would have a higher melting point? Higher melting point. You can either unmute your mic or type it out.
The saturated one?
Yeah, exactly. Exactly. We're going to put here higher melting point because fully saturated. Remember this, Tony? One night I went on a big thing where I said, okay, well, if you have, 1 double bond, it lowers the melting point. If you have 2, it lowers it even more. Yeah, absolutely. So again, you can think about this in terms of the efficiency of packing. If I have a bunch of these molecules, they're going to pack together much more efficiently than these ones will with this crook in it here, so to speak. Okay, so that's why saturated fats are solids at room temperature, where unsaturated fats like oils are, generally speaking, liquids at room temperature. Okay, let's move on and keep going here. Question number 39. This one involves a little bit of nomenclature. And it says here, the acid hydrolysis wants us to draw the products of the acid hydrolysis of 2-methylpropyl ethanoate. And we just went over this earlier. Ethanoate, this is an ester. So you have to know your ester nomenclature. Let's start by drawing it out. If it's ethanoate, I need 2 carbons, right? Eth is 2, and it's an O8. And then the alcohol part comes from this 2-methylpropyl. So 1, 2, 3. And on the second carbon, I put a methyl like this. And what are we doing? We're hydrolyzing it in acid. So we're heating it up in acid. We'll put here, all right, heat, and we're going to break that apart. Where are we going to break this? I went over this many times in class, but let's go over it. And I'm going to just turn on the heat here. It's really hot. And we'll take a look at which bond is going to be broken. And I'll tell you right now, it's one of the bonds between carbon and oxygen. And which one do you think is going to be weaker, a double bond or a single bond? Well, it's the single bond that's weaker. So the bond that's going to be cleaved or broken is this bond here that I've highlighted in green, which would leave us with this and this. Okay, but how do we make an ester? Right? If you remember esterification comes from the condensation reaction between a carboxylic acid and an alcohol. And this is the opposite. This is the hydrolysis of an ester, right? This is hydrolysis of an ester. And how does that happen? It's when you take an ester and you heat it up with acid and you form a carboxylic acid and an alcohol. You see those atoms that I highlighted in blue? What do they make? H2O. Because that is what you add to the molecule to blow it apart into the carboxylic acid and the alcohol. So this, again, is a carboxylic acid. Let's just, now we can do better than that. This is acetic acid. And this is 1, 2, 3. This is 2-methyl, 1-propanol. Okie doke. Draw the products of the base hydrolysis of butyl acetate. Same type of deal. So first we're going to draw butyl acetate. So acetate has 2 carbons. It's the common name, acetic acid, which has 2 carbons. So acetate, and then butyl. So 1, 2, 3, 4. I'm taking that. I'm treating it with base. I'll just put hydroxide, and I'm going to heat that up. But I'm not going to end up with a carboxylic acid, am I, if I'm in strong base? I'm going to end up with a carboxyl 8. So I'm going to hydrolyze this bond here, and I'm going to end up with, I'll draw it in blue because it's easier to see. I'll end up with acetate plus an alcohol. Okay, so we'll put here acetate, and this would be 1-butanol. Okay, now if you're wondering, why is there just a negative charge? Where's the positive charge? I didn't write it in, okay? If you want to put a cation, if you want to put, okay, it's sodium hydroxide, no problem, then this would be sodium acetate. But the reason I didn't do that is because organic chemists love to leave out spectator ions. We like to leave them out of our reactions. The next question is question number 40. This is a little bit of exercise in drawing. Some of these are more complicated than others, but let's just think about them rationally and see if we can come up with some good answers. The first one is cis 1,2-diethyl cyclopentane. I'd start by drawing the parent, which is cyclopentane. So I have a cyclopentane, so I just draw a pentagon. Then I have 1,2-diethyl, but they're cis, so that means they're on the same face of the molecule. I'm going to draw it with a wedge. If you wanted to draw it with a dash, that would be perfectly acceptable. So there we go. There's cis 1,2-diethyl cyclopentane. The next one, it looks long, but let's just approach it rationally. So we have 5-bromo. Then we have a 3-isopropyl. There's a double bond in the molecule, and they're telling us that it's a trans hex-2-ene. And then I have a 2-thiol. Now, I don't know if you remember what a thiol is, but a thiol is when you have, it's like an alcohol, but instead of an oxygen, you have a sulfur. That's a thiol. So let's start by drawing the parent chain, which has 7 carbons and has a trans double bond at the second carbon. So let's see here. So I have 1, 2, and there's my double bond, 3, 4, 5, 6, 7, like that. Then what else do I have? I have a 5-bromo. So let's number these. I have 1, 2, 3, 4, 5. So I'll put a bromo down here. There we go. I've got a 3-isopropyl. So we'll draw the isopropyl like this. And then what else do I have? I have a 2-thiol. So we'll put the thiol up here. If you saw the molecule, if you just saw this molecule and somebody said name it, that would be tricky, I think. But when you see the name, it's much more evidently clear how to draw the molecule. The next one is an ether. It's 2-methylpropyl, 2-chloropropyl ether. So we're going to have an ether. So we've got 2-chloropropyl or 2-methylpropyl. So let's start with that. So we got a propyl, and then we have 1, 2, so 2-methylpropyl. And on the other one, we have 2-chloropropyl. So we have 1, 2, 3 carbons. And on the second one, we have a chlorine. Chlorine, there we go. The last one is 4-amino 5-hydroxy octanoic acid. So hydroxy is the same thing as just an OH, okay? And it's an octanoic acid, so that means it's a carboxylic acid with 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. Like that. Sorry, I kind of spliced it together there. And then we've got a 5-hydroxy and a 4-amino. So 1, 2, 3, 4. So we have the hydroxy. Nope, shit, that was supposed to be the amino. Pardon my language. Put that there. And then we put our hydroxy like that. There we go. Next question deals with esters. No, it deals with the carboxylic acid. A lot of questions about esters on these exams. Industrially, we often need ethanoic acid. So ethanoic acid is the same thing as what? Acetic acid, which is the main component of vinegar. The starting material for this product is usually ethylene. So ethylene or ethene is this molecule, CH2CH2. Show below a series of reactions that would transform ethene to ethanoic acid. Well, the first thing that I would do is reopen this. I'm going to go back to wherever the heck I was. Here we go. Okay, so I want to take ethene and I want to convert it to ethanoic acid. Well, this is one of those questions that seems more complex than it actually is. Let's just write it down here. I'll erase all this. So I'll show you how you should do this. You would start with ethylene and you would treat it with a catalytic amount of acid and water to do a Markovnikov addition, and you would end up with ethanol, right? So you end up with ethanol, and what would you do then? You would just oxidize the heck out of it, right? Strong oxidizing agent, and you would end up with acetic acid like that. What is saponification? I told you have to know esterification, saponification. Saponification is the hydrolysis of an ester, but what? Who can tell me? What am I missing? In what?
Is it an acid?
No, it's not an acid.
Base then.
Yeah. Yeah. Saponification occurs in base. Right? Saponification is how the pioneers made soap, and they made the base from the ashes from a wood fire and from rainwater. So they isolated lye, which is the same thing as base. So saponification is the hydrolysis of an ester in base. When you hydrolyze an ester in acid, it's just called the acidic hydrolysis of an ester. Not very exciting, huh? Anyhow, oops, no, that's not what I meant to do. What type of biological molecules includes many hemiacetals? This is supposed to be a one-word answer. Who could tell me?
Sugars.
Yeah, carbohydrates, yeah. Done. So there's a hemiacetal, right? Carbon, oxygen, hydrogen. So the answer for this one is carbohydrates. There you go. Nothing more than that. Next one's a little bit of nomenclature practice. The first one is a cyclic ketone. So this ketone has 5 carbon atoms in the parent, so that would be a pentanone. So this would be a cyclopentanone. And of course, the carbon with the carbonyl is carbon 1, so we go 1, 2, 3. Because if we had gone in the other direction, it would go 2, 3, 4, which gives the methyl group a higher number. So we'll erase all that. And therefore, this would be 3-methyl cyclopentanone. The next one is a cyclobutane. It's got a bromo at carbon 1 and at carbon 3. But remember, like we saw earlier, it's very important that you point out that these 2 bromines are on the same face of the molecule. And the way we designate that is with cis. So these are cis 1,3 dibromo cyclo, and there's 4 carbons in here. 1, 2, 3, 4. It's a square, so cyclobutane. I'll give you a second to think about the next one. I want you to try to come up with the common name for this one. And while you do that, I'm going to erase something here. I made a mistake. All right. So this is an ester, and this would come from formic acid and ethanol. So this would be ethyl formate. Ethyl formate. Again, that would be the common name. I'll just do it color coded. And then if I want to use want to give the IUPAC name, this would be ethyl methanoate. All right. Okay, the next one, I would only expect you to come up with the common name. And the reason why is because this one was a reagent that we looked at briefly. Does anybody recognize the functional group in this compound? What's the functional group? Does anybody recognize the functional group in this one? I could highlight it for you. It's this part here, and then if I have an R group here and an R group there. Anyhow, that functional group is in, let me get this, there we go. It's an anhydride. So this is acetic anhydride. The next one has a parent in it that we saw before. So this part here, this is called Anisole. And so this would be carbon 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So this is 2,6 diethyl anisole. And the next one is an amide. And we spent some time one night going over amide nomenclature. And since there's 2 methyl groups on the nitrogen, This becomes NN-dimethyl. And since I have 3 carbons here, we have carbon 1, 2, 3. This becomes propionamide. So NN-dimethyl propionamide. NN-dimethyl propionamide. All right, there we go. So with that in mind, let's take a look at this. Question number 45 is kind of a goofy question. I'm guilty. I came up with this one. It's too ambiguous. There's just too many different things that we've looked at. It says name a reaction that could be used to destroy or react away the following types of molecules. I don't know. You burn all of them, right? With the first one with an alcohol, right? If we have a primary alcohol, we could oxidize that to a carboxylic acid or to an aldehyde. Put an aldehyde. If I have an aldehyde, how do I convert that to a primary alcohol? I do that by hydrogenation, right? Hydrogenation of a carbonyl. A carboxylic acid, I could take a carboxylic acid and I could do a reaction with an alcohol like ethanol, and I could treat that with acid and I could heat that up to do a esterification reaction, and I would end up with an ester like that, ethyl acetate. And then an alkene, like let's say I had propene, I could treat that with hydrogen and nickel, and I could make propane. Anyhow, kind of a goofy question, but I made it a long time ago. I think like the second time I taught this class, just to get my students to think about different reactions they had learned. But this next one I think is a good question. It says rank the following 4 molecules in terms of boiling point. So going from highest boiling point 1 to lowest boiling point being 4. So who can identify the functional groups that we have in these? Because these are condensed formulas, and we don't actually spend a hell of a lot of time looking at these. There's more of them in the textbook than there are in our class. Anyhow, this one has an ester in it, right? So this is the condensed form of an ester here. This one is an ether. This one is a ketone. And then finally, this one here is an alcohol. Now you can probably all figure out that the alcohol is going to have the highest boiling point because it's got hydrogen bonding, so it's going to have the highest. And the ether is going to have the lowest boiling point, and I explained why that is earlier on. And then between the ester and the ketone, I wouldn't care which one you put is number 2 or number 3 because it's very difficult to distinguish between the boiling points of esters, ketones, and aldehyde. Very tricky and able to be able to do that. So I would accept 2 or 3 or 2 or 3, just like I did on the exam. I said if you put the aldehyde in the ketone one way or another, it doesn't matter. Either way is going to be okay. Just as long as you understand name the molecules. Name the molecules in 46. Well, let's do it. I'm in the order that they're in here. So the one on the top left is an ester. It's got 2 carbons for the carboxylic acid and 2 carbons for the alcohol. So it must be ethyl acetate or ethyl ethanoate. Either one works. The next one I have 1, 2, 3 carbons, and the alcohol is on the second carbon. So this is isopropanol or 2-propanol. We could put here 2-propanol. We'll put here isopropanol. Okay, the one on the top right is diethyl ether because it's got 2 ethyl groups on the ether. So this would be diethyl ether. It's one of the most commonly used ethers in organic chemistry. And the one below that, I have 1, 2, 3, 4. So my ketone is on the second carbon. So you don't have to call it 2-butanone because there's only one place to put the carbonyl in a 4-carbon ketone, and therefore this will just be called butanone. Butanone. Like that. Question number 48. Draw an example of Enol, keto-enol tautomerization. This is also something we looked at this morning. I think the best thing for you to be able to do would be if I were to give you an enol like so, and I said, okay, well, draw the keto form of it. Okay, well, you should be able to draw the keto form because there are only 1, 2, 3 carbons in the molecule. So I will say 1, 2, 3. And then instead of being a single bond to my oxygen, now it's going to be a double bond to my oxygen like this. And then I move a hydrogen around. That's it. So this would be the keto form, and this would be the enol form. Draw the following molecules. A little bit of alcohols nomenclature. So let's give them all a try. The first one says 3-ethyl, 5-cyclopropyl, 2-pentanol. So it's a 2-pentanol. So if I have 1, 2, 3, 4, 5 carbons, on the second carbon I have an alcohol, 2-pentanol. So that would be just 2-pentanol. Then on the third carbon I have an ethyl group, so 1, 2. And on the fifth carbon I have a cyclopropyl. So cyclopropyl is a little triangle dangling off the end like that. There we go. So 3-ethyl, 5-cyclopropyl, 2-pentanol. Is there a mistake in that name? Anybody notice that there's a mistake in this name, the way that it's written out?
Is it the C comes before E?
Yeah, I just noticed that. Yeah. I started writing the molecule. I'm like, wait a second, that's not right. What kind of hobo put this together? Okay. So I think it's Sean, right? Is that you, Sean?
Yeah, I was the one that said that.
Yeah. The cyclopropyl should come first. Whoopsie doodle. And, yeah. Okay, there we go. I'll have to fix that in the next version of this. So cis 6-methyl-3-heptenal. So again, these things seem really complex when you look at them, but if you break it down into something simple, it's a 3-heptene al, so it's an aldehyde, right? It's an alkene at carbon number 3, right? 3-heptene al. So we'll start with drawing an aldehyde, and then we say 1, 2, 3, and we'll put a double bond, 3, 4, 5, 6, 7. There you go. And it says it's cis. Shit. 1, 2, 3. So I'll erase the rest of this spinach. Sorry. There we go. And then it has a 6-methyl. So we say 1, 2. Nope, didn't mean to do that. Still had my eraser. So we have 1, 2, 3, 4, 5, 6. There you go. Very reasonable compound to draw. Man, I've got all kinds of mistakes in my solutions here. I must have done them way too fast. The next one, 2,5,6-trimethyl, 2,5-heptadiene. We don't look at a lot of compounds with double bonds and ketones in them. Well, let's see if we can do it, okay? So it's got a double bond in the 7-carbon chain, but it's got one of carbons 2 and 5. So let's see here. 1, 2, double bond. 3, 4, 5, double bond. 6, shoot, it's kind of long. There we go. 6, 7. Okay, we got that far. So, and then it says 4 ohm. So that's a ketone, right? So 1, 2, 3. No, what am I doing wrong here? 1, 2, 3, 4. Yeah, that's right. 1, 2, 3, 4. Okay, we got that. And then we have 2,5,6-trimethyl. Let's just fill them in. 1, 2, 3, 4, 5, 6. Done. Do I have an extra carbon here? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got 2 extra carbons. What is this guy smoking?
It's a Monday.
Yeah, thanks. Whoever said that, I appreciate your patience. I'm tired. I was just I got 2 truckloads of mulch today and dumped them all out, and then I came in and showered and came to class. So let's see here. 1, 2, 3, 4, 5. Oh, there we go. 6. 1, 2, 3, 4, 5, 6, 7, 8. No, what the F am I doing? 1, 2, 3, 4, 5, 6, 7. Okay, so that's right. Then we need a ketone at carbon number 4. 1, 2, 3, 4. There we go. And then 1, 2, 3, 4, 5. There we go. That looks more like it. Whew, sorry about that. What time is it? 7-Eleven. I think I need to hit up the 7-Eleven. I didn't have my, normally I drink 2 cups of coffee a day, and I didn't drink my second one. Big mistake. Anyhow, cis, 6-bromo-2,4 hexadienoic acid. Shoot. Okay, so it's a diene, and the 2 double bonds are at carbons 2 and 4 of a 6-carbon chain, and they're both cis. So we'll put 1, 2, 3, 4. We can still draw it this way. 5, 6, and then I have a bromine on carbon number 6. Done. Okay, not nearly as bad, right? You get it? Hopefully you get it that this is a cis double bond, and this is also a cis double bond, like that. This is a good question. Okay, now you won't have to draw any hemiacetals on your exam because it's multiple choice, but I would still like you guys to practice them, you know, to be able to draw a hemiacetal. It says draw the reaction of propanol with 2-propanol to create a hemiacetal. And we went over this quite a bit in class, so I'll go over it kind of quickly here. But if we have propanol, so if we draw propanol, so that's a 3-carbon aldehyde, propanal, and we treat that with 2-propanol, which is isopropanol. Okay, we treat that with acid, catalytic amount of acid. And I think I went over this in class, how, you know, this lone pair attacks this carbonyl here and breaks this double bond like this. So then what happens is we could draw those 3 carbons from the propanol, and then we put the oxygen up like this. Let me color code it just for interest's sake. No. There we go. And there's my isopropanol. So then what's going to happen is I'm going to have my isopropanol attached like this, and then I'm going to have a hydrogen up like this. Now this hydrogen here, okay, I could highlight that maybe in yellow. That's this one, which is right here. So this is the hemiacetal. Now I asked you to draw this. I think it was on exam. It was our last exam that we had before the face-to-face class is ended. So make sure you can recognize a hemiacetal in an acetal. Now this question doesn't ask us to draw it, but of course this could react again with another equivalent of the alcohol. It could form an acetal. So the acetal would look like, it would look like this. It would look like this, and then of course it'd have my hydrogen like this. So this would be the acetal. Anyhow, why are carboxylic acids more acidic than alcohols? This is a good question. So if we draw a carboxylic acid, okay, what's the definition of an acid? Okay, loses H plus. If a carboxylic acid loses an acid, I get a carboxylate. And if an alcohol loses a proton, I get an oxide like this. Who can tell me why the carboxylic acid is more acidic? What's the difference between these 2 conjugate bases?
The double bond of oxygen.
Yeah, it's resonance, right? We could put here conjugate base is resonance stabilized, right? So this structure, the acetate, you could also draw it with the negative charge up here and the double bond down here. Whereas this, you cannot do it with an oxide like that. So resonance. Oh, I meant to highlight that, not draw a line through it. Oops, I'm losing you guys. There we go. Resonance. Make sure you look over the concept of resonance because you go over that even in Chemistry 101. I'll do this quickly and then we'll call it a night because I wanted to talk to you guys just for a second. Draw the enantiomer. Oops, crap. To draw an enantiomer, all you have to do is flip all the dashes and wedges. So if I draw this, all I have to do is draw a dash and a wedge, and then I just flip them. So I put the hydrogen here and the OH over here, and this is the enantiomer. Another way you could do it is to draw the mirror image of it if you want to do that, but it's more painful to do that. So there we go. An enantiomer is non-superimposable mirror image. Okay. All right, that takes us to 7:16, and I wanted to speak to my students for a minute. So bear with me for a second here. Stop. And done. And then I will go to here. And back here. And then